Okay, welcome to the last episode of Hottest for this season. Today we are happy to have Mitchell Riley from NYU Abu Dhabi, who will be telling us about tiny types and cubical type theory. Please go ahead.
Okay, thank you very much, and thank you for the invitation. So I'm going to be talking about an extension of type theory that I've been working on, which adds a tiny object to ordinary dependent type theory. And once I've introduced the type theory and sort of explained how you might use it, I'll try to give an indication of how it could help us implement cubical type theory. So first of all, what is a tiny object? Well, it's an extremely simple definition. A tiny object in a category is one where when you form the functor that forms functions out of that type has a right adjoint. Now, of course, we expect it to have a left adjoint, and the amazing thing is that it has an adjoint on the other side. And so in sets, only the singleton sets are tiny. And so in some sense, being tiny is a bit unusual if we're looking at models of type theory, but there are lots of settings where there are non-trivial tiny objects. So I've got a few of them listed here. First of all, in many different versions of cubical sets, the interval is tiny, though not all of them. The original example of a tiny object, and the one that motivated it being studied in the first place, is in synthetic differential geometry. There is a type called the infinitesimal disk, which is all of the real numbers which square to zero. Now, this certainly contains zero itself, but also some sort of infinitesimal fuzz. And this type altogether is tiny. Another example with a different flavor is in the topos that classifies the theory of an object. So that's just as a category, that's the functor category from finite sets to sets. That classifying topos has a universal object in it, which turns out to be just the inclusion of finite sets to sets, and that is also tiny. And a general statement, which sort of encompasses several of the previous ones, is that if you're looking at a presheaf category, then if the site has finite products, then every representable presheaf is tiny. And you can show this just by a direct calculation, like you can calculate what this right adjoint must be. Okay. So I'll briefly say something about the original motivation for studying these tiny objects. So that's in synthetic differential geometry, although I won't say very much about this. We think of this infinitesimal disk, this infinitesimal neighborhood around zero, as sort of being the walking tangent vector. And if we map from this infinitesimal disk into some other type, some space, we think of it as picking out a point, which is where zero goes, and then also choosing an infinitesimal direction around that point, which is mapping where the fuzz goes. So the tangent space corresponds to just the ordinary function type from this infinitesimal disk into the space that you're interested in. Then in differential geometry, you're interested in forms, which are maps, say real valued maps on the tangent space. So in this setting, you end up with maps from that type of functions into the real numbers. And if this infinitesimal disk is tiny, then we can transpose that map like that. And forms will correspond to maps from the space that you're interested in into this sort of very unusual space, which is the amazing right adjoint applied to the real line. And so this is now a single object which classifies some kind of form on anything that maps into it. And this is the kind of thing which can only exist in synthetic differential geometry and doesn't work classically. Okay, so I want a type theory which lets me talk about a type that has this property of having this amazing right adjoint. So I have some requirements for this type theory. So I want rules for a right adjoint to this formation of function types satisfying. Well, first of all, I want to avoid requiring any axioms in this type theory because I want everything to compute as much as possible. I don't want to get stuck on axioms. I want to allow the tiny type to be just an ordinary type. And this is especially important for this for things like synthetic differential geometry, because I mean, this type that we're interested in is something that we can just describe inside the type theory already. And so we don't want to be forced to have this tiny object be like somehow treated specially, or a pre-type, or something that's not allowed to interact with the rest of the type system. I want the rules in this type system to be comprehensible, relatively speaking, or as far as we can make them, because I want people to be able to use the type system, both informally, like I want people to be able to do these kinds of differential geometry arguments. So like, in an informal style using words, and also in a hypothetical proof assistant. And so for the latter, we're going to need at least a plausible type checking algorithm for whatever this type theory ends up being. So I believe that I've met these requirements, and I can leave it to you to judge whether that's true by the end of the talk. So I'll very quickly say something about other people who have thought about similar problems. So sort of the earliest thing that I'm aware of in type theory that does this is this Lops paper on constructing universes that classify vibrant types when they're trying to build models of cubical type theory internally. And for that, they end up using this amazing right adjoint in an important way. And the way they do it is they add in a bunch of axioms. They just assert the things that they need. And not only that, but to make this work and to not sort of accidentally trivialize this operation, all of these axioms are guarded by a use of this flat modality. So they need to work in crisp type theory to make sense of this. They need to make sure that any input to these axioms is a global type. So it's sort of quite restricted in the ways that they can use this. So David Jazz has done some work on synthetic differential geometry, and he improves this axiomatization by, rather than just putting the entire adjunction in at once, he instead asserts that there's a co-unit map, and then that the induced map between the Hom types is an equivalence, the one that comes out of this co-unit. And the reason to do this is that you end up with a more coherent adjunction, because you're sort of piggybacking off the coherence of the forming function types. But again, this has to be done in crisp type theory to make sense. So Neutz and De Vries have a line of work where they try to come up with a type theory for a related operation, which is a right adjoint to some kind of telescope quantification, where they take a chunk of the context and say that they can look at functions from the tiny type into that whole chunk of the context. And in fact, Andres talked about this yesterday, and I haven't yet digested his talk, so I can't say much about how that relates. But the things that they've been working on, it's easier to tweak the kinds of tininess that they're interested in, but the rules are quite complicated, and I'm not sure that they've thought about how to use it informally, or type checking algorithm, or things like that. Although I'd love to know if they have. And finally, in recent work, Gratzer, Weinberger, and Buchholz, in their simplicial type theory, they're doing some synthetic higher category theory. And to get all of the operations that they need, they work inside this multimodal type theory with a whole suite of modalities. And to end up with one of them representing this right adjoint, they add an axiom that says that one of these modal operators on the context is exactly the same as context extension. And I imagine that this axiom would really mess with normalization algorithm, but they're using a bunch of axioms in their formalism anyway, so it doesn't really matter for what they're doing. Okay, so Now I'll turn to the type theory that I'm suggesting for this setting. Okay, so I'm going to build up to it in stages. I'm going to try and ease everybody into it. I'm going to start with just a right adjoint that everyone's familiar with. I hope that you'll agree that these are just the totally ordinary rules for the function type. So just so that we don't get lost in the specifics of syntax, I'm going to change the name of like the lambda binder just to lam and the application into app. So in the rules for the function type, we can see that the introduction rule is exactly one direction of the transposition operations. Like we go from this left adjoint operation on contexts to this right adjoint operation on types. But the symmetry is broken in the application rule, where here we start with this, but we don't end up with something on the bottom, which is gamma comma x in A down here. And the reason for this is that it's very unpleasant in type theory to have rules where the context in the conclusion is not as general as possible. So if you imagine having the variable down here, what happens is that we build a substitution for that extra variable into the rule. So that explains this assumption here. So my next step here is going to be to undo that move and just instead keep this rule the same and change this rule so that it's just purely an inverse to the introduction rule. Sorry. And just before I move on, I'll say that if we think about what happens when we build the substitution in for this variable, that shows up both in the type of the conclusion over here, because we've gone from B depending on X to just X gone. We've used the substitution, but it also appears in this computation rule. If we think of the substitution as kind of being stuck on this application, then once we do this beta reduction, we've sort of released ourselves from this stuck situation, and the substitution that was waiting can now actually happen. Okay, so here's where we are. We have these rules as just perfect inverses to each other. The next step is to generalize to now just some general left adjoint operation on context and right adjoint operation on types. So this is no longer a context extension and the function type, but the rules are the same. They're the same form. It's just the pure transposition operations. And here I'll just say that I've written the left adjoint operation on contexts sort of as though it's a context extension, where sort of by comma L, what I mean is we're applying the L operation to gamma, just to explain why this is on the right here. And so rules like this are roughly what happens in this paper on dependent right adjoints. Again, we've ended up with this rule with something which is not fully general on the bottom of the rule. But here, there's not really anything we can do about it. The best we can do is we can make the conclusion slightly more general by building in weakening to make weakening admissible again. But we can't get rid of this this L that's in the conclusion. One of the innovations, so we're going to move on to the next step. So one of the innovations.
Sorry, real quick on the. Sorry, Mitchell. Yeah. What exactly how should I think about the L not in gamma prime?
Well, here I'm only allowing ordinary weakenings of additional variables here. So a way to think of it is if we take this rule here, I'm precomposing it by the projection from the version of this context with a bunch of extra ordinary variables. And I can't have any L there because there's no way to sort of project away the additional L's just for some arbitrary.
Got it. And I should think about the variables in gamma as being under L. Yes. So when I write, gamma comma L, I think of those as being under L, and then these new ones are not under L, is what you're saying.
Exactly. Yeah. And that sort of writing it in this way, I find helps keep track of like what's affecting what as you move from left to right.
Thanks.
I actually have a follow-up question on that. So I can think of that as this is like L of gamma times, like parentheses, times gamma prime, right?
Yes.
Or
Yeah.
and but I mean gamma prime could be of the form L of something, I suppose, right? Or you're saying that's not allowed.
I'm not going to allow that. I'm only going to allow applying a context operation to the entirety of a context and not a telescope. And
Okay.
And not, I'm also not going to allow like the comma of two completely independent contexts, which is kind of what you're suggesting.
Right. Yeah.
I think.
Okay. I see.
Yeah.
Yeah.
Okay. So the next step is this paper where they call their type theory Fitch TT, where they sort of they resolve this problem by noticing that if they're in a situation where they have a triple adjoint, so if the left adjoint operation on context has a further left adjoint, we can fix this issue because there's now a universal way to solve this problem. If we, before I look at that, we now have these two operations on context which are supposed to be adjoint to each other. And the way we're going to implement that is by these rules down here for that correspond to the unit and the co-unit of this adjunction. And so what the unit of the adjunction should give us is a map from gamma into gamma, comma, E, comma, L. So this is kind of the downside of writing these things postfix, is that this maybe looks backwards to what you would expect. But what this rule will correspond to is if we can produce something in this context, we can pre-compose it with the unit substitution to get something just in gamma. And the same is sort of true for the co-unit. If we now have any judgment in any context, then we can pre-compose it with the co-unit substitution to get something like this down here. So now if we take the input to this rule, to the elimination rule, as already being in a context with E applied to it, then we can build this unit substitution into the application rule. Oh, sorry, into the elimination rule. So that'll look like this. Now we've sort of corrected the context that appears in the conclusion, and the correction that we've made appears in the same places. So it appears in the type here. We've now done the same sort of pre-composition by a substitution here. And again, now when we use the computation rule, this unit that got built into application now becomes unstuck as soon as we have the things line up correctly. Okay. So now I'm going to take that setting and specialize it to the tiny type, the thing that we're actually interested in. So not really much has changed here. Now we've got this triple adjunction where the leftmost one is context extension with the tiny type. The middle one is something that should be an operation on contexts corresponding to maps from the tiny type into the context. So this is just like, comma L or something in the previous slides. But now I'm thinking of it as being like functions from the tiny type into the stuff that comes to the left of it. And then the right adjoint operation on types is the sort of the whole reason we're doing this in the first place. Right. So not really anything has changed, except I've changed the symbol for the lock. And now everywhere we had E on the previous slide, we now have just an ordinary context extension with the tiny type. Okay. All right. So on the next slide, I'm going to, the next step is to, I'm going to replace just the lam and the app text here back with the syntax that I want to use for these things. And now there's good chance that this is the part of the talk where people will get upset, but I'm going to try and justify why I want to write things this way. Okay, so here, these things correspond to lambda and application. So what I want to do is I want to write the introduction rule for the root type as being like a binder. We've sort of bound this lock. When we go inside a term like this, what that means is we've got the lock sort of moves into the context, and then we proceed into the body, right? And now the other rule I want to write as a kind of application, right? So the reason for this is that I want when these things come together, I want it to look just like applying a function to an argument in the ordinary way. So here I've got an element of the root type, and I'm applying it to an argument of this strange kind. And so what's happening here? Well, just going back to what the rule on the previous slide is, what happens inside an application is that the term that you're applying now has access to an additional assumption that it didn't before. This is very strange. The application is now binding a new variable. And so I'm writing that like this. The application is the thing which is now binding a variable which is available in the term R. And what's weird about this is the variable is bound here, and then we're allowed to use it over here. And this is strange, but I mean, hopefully in the examples, which I'm going to show in a second, you'll be convinced that putting up with this weirdness is nice enough to so that everything lines up with function, like the ordinary function application. Okay. So over here, on the right here, we have the syntax that I want to use for the unit, which is sort of strange and unpleasant. Oh, sorry, I should have said before I move on. The reason I've written like this is it's just an upside down lambda. I'm trying to remind everyone that the variable here is now available in the opposite direction to the one you expect. Okay, so that explains that. Okay. So the unit I want to write like this, because this is exactly what the function application syntax should lead us to. We've got something that looks like a lambda, something that looks like an argument, and then what comes out of it is an application of the unit. So I want to write that as though we're substituting this thing for this thing. This new bound variable for the lock. Okay, I know this is very strange, but I'm going to leave these as many of these rules as I can sort of up on the slide in the future slides, so that you can sort of look at them as you need to. Okay, so I'm going to talk more about the co-unit in just a second. So before we move on, there's one last thing, which is that in a general term, we might have lots of locks running around if these things become nested. And so we might want to refer to them by a name, just so we can tell which one we're talking about. But for most of the examples, I'm going to leave it off because there's only one lock that we have to worry about. Okay, so let's look at this co-unit rule. I haven't justified yet why I've written it like this, but that's what I'm going to try and do now. So this rule is much like the original function application rule that we had, where we've now got this extra variable stuck in the conclusion, and we can sort of fix that easily by building in a substitution for this this extra assumption. So that's the first thing we're going to do. And then again, we're in a setting where this conclusion is not fully general. So I'm going to do the same thing as we did for the dependent right adjoints and say, okay, we're going to build in some weakening here for the context in the conclusion. So again, for this to make sense, we need to not have any locks in the telescope here. We just want ordinary weakenings. Okay, so how do we think about this rule? Well, here's how I want to think about it. Over here, we've got some judgment which we've built just using stuff in gamma. And now we want to use that construction in this extended context where we've now got a lock to the right of the gamma that we started with, right? So we shouldn't be allowed to use that construction directly. We're going to have to do something to it to sort of get it out from behind that lock. But now the thing to remember is that the meaning of a lock is that it's a function from the tiny type into the context that comes before it. So as long as we can provide an argument to that function, which is exactly this thing here, then we can apply the function, get the stuff from gamma that we need, and then we have our construction in the overall context. So I'm thinking of this as saying we can use elements of T as sort of as keys to get us past any locks in the context that we want to. Okay. Okay, so up here, I've just got the rules copy pasted from the previous slide. There's nothing new there. I just want to do a bunch of easy examples to try and get a feeling for what this is like to use. Okay, so first of all, if we have an element of root A, then we can extract from it just an element of A. So how do we write this in syntax? Well, we've got our element of root A R, and we just apply the eliminator immediately. So the eliminator, inside the eliminator, we gain access to an additional argument, so an additional assumption of the tiny type. So that's the thing which is bound here. But we don't have to use it at all. I mean, we've already got an element of root A, so we can just apply the eliminator directly and get it out. And so this is just the same as like if you're forming like a constant function where we're absolutely allowed to bind a new variable and then not use it if we like. So I think of these things as sort of dual to each other. Okay. So now I want to do functoriality, and I'm going to use this and attempt to demonstrate how you might sort of explain a definition like this in words. So the block of text doesn't look very good on the slide, but I'll just talk through it. Okay, so we're going to start with some defining functoriality. We're going to start with just a function from A to B, and we want to define root A to root B. So this is just an ordinary function, so we'll assume that we have an element of root A, and we're going to try and get root B. What the introduction rule says is that it's going to be enough, if we want root B, it's going to be enough to produce an element of B after we lock all of our assumptions. In particular, the R that we started with is now locked. Okay, we're trying to get B. Because we have this function available, we just need to get an A. So our new goal is just an A. It would be nice if we could use the map from the previous slide, which just lets us extract the A from root A. But we can't do that because we've now locked our root A assumption behind the context lock. And so if only we could unlock that, if only we had an element of the type, then we would be able to unlock the element of root A so that we had access to it and apply the eliminator. But the fact that we're applying the eliminator amazingly means that we do have this assumption of the tiny type that we need to unlock the term that we're applying the eliminator to. So sort of in syntax, you can see it here, but also here, we're applying the so sort of speaking in the other direction, we're applying the eliminator, which gives us access to this assumption of the tiny type. And then we can use that assumption to unlock the thing that we're applying the eliminator to. So now we've got an element of A, and we can apply the function to it. And so that completes the definition of the map. So this is sort of the way I think about this when I'm trying to like construct something in this type theory. You sort of imagine, well, like, what if I did have an element of the tiny type? Then could I, use that to do something useful and get an element of the root? Because if I can, that means I can sort of thread that element, thread the amazing argument to the eliminator for that root back into the thing, the places where I've just needed an element of the tiny type. So I'll do some more examples just so that's a bit more clear. So I'll just say that this this is just the same shape of a definition as postcomposition. So here we're just sandwiching the function f between the introduction and the elimination rule. The only weird thing which is happening is this funny sort of the co-unit giving us access to R. but it's the same shape of definition, is what I mean. So I'm just going to add in a little bit of syntactic sugar, where so if we look at this definition, which the last couple of definitions that we did, just sort of without thinking, we wrote this definition without using the actual lambda symbol. We just sort of wrote a list of arguments to the function that we're defining. And I want to do the same thing for when we're defining an element of the root type. I'm just going to add a lock into the argument list. So the reason I find this readable is that if we've got some complicated function with many arguments and many things locked, it's really easy to tell what variable is locked by which lock, because each lock just affects everything to the left of it. So this syntax lines up, it makes sense when combined with ordinary function application. So if we imagine later on, we take this definition and then we apply it to some stuff like this. So this is an ordinary argument and a lock. So we apply it to an ordinary term and this amazing binder. Then what happens is, well, the term gets substituted for the variable, just like normal, and the binder gets substituted for the lock, like this. So everything sort of clicks together the way that you would expect. Okay, and this sort of, it's just a bit of syntactic sugar. Okay, so let's do one more example of this weird sort of backwards threading. So the point of having this right, or one of the points of having this right adjoint, is that it makes functions out of the tiny type a left adjoint. And so it now preserves colimits, in particular sums. And so there should be this sort of unexpected map, which is the opposite to the split map that you would expect. We should sort of somehow be able to do case analysis on where this function goes. Either it goes into A or it goes into B. So this is what Andreas Neutz calls high dimensional pattern matching, which seems like a reasonable name. Okay, so the way you would be expecting this argument to go. Oh, sorry. I just scrolled way too. Okay, sorry. There we go. The way to be expecting this argument to go is, well, we use the adjunction to get this T arrow out of the way. Then we do case splitting on here, and then we move the right adjoint back. And so that's basically how this is going to go. But here's how it looks sort of in syntax. So I'm just going to define the transposed map directly, because it's sort of much easier. Here we've got, we're just going to pattern match on the sum. And then in each case, we're producing an element of the root. So we immediately lock in both cases. And then in the left case, we're certainly going to end up in the left case over here as well. So we need to just come up with a function from T to A. So binding in, like just doing a regular function lambda abstraction for the element here, this element of T is exactly what we need to get access to this element of A out here. Otherwise, we wouldn't be able to just like use A over here. And sort of similarly for the right-hand side as well. The fact that we're defining these functions is what lets us get the B from out there. And now sort of using the same reasoning as the earlier example, if only we had an element of the tiny type that we could apply this function to, then we would have an element of A plus B that we could just use the lemma with, right? But because the thing we get out of the lemma is this element of the root, then when we do the eliminator for this element of the root, it like amazingly gives us the assumption of the tiny type that we needed to use this function in the first place. So it's this strange sort of backwards threading. Okay. All right. So I haven't really said anything about what these unit and co-unit operations do. So we need them to, at the very least, relate to each other to make the to give us the context extension lock adjunction that we would expect. Well, so first of all, the unit and the co-unit operations commute with all of the ordinary constructions of type theory. So we can just sort of push them through other things as needed. So, but something interesting has to happen, and it happens when a unit meets a co-unit for the same lock, of course. So when this happens, and this might happen when you do when you end up with a beta reduction for the root type. You create one of these, which might end up meeting one of these. When this happens, it turns back into a regular substitution. So sort of writing out the derivation trees here, say we've got some judgment, which uses this assumption I, and then we use some term to get it out from behind this lock, and then the unit lets us sort of kill both this lock and this assumption at the same time. Then the result is we just take the original term and we substitute the t that we use to unlock the judgment j in the first place. So this corresponds to the triangle identity, or one of the triangle identities for this adjunction, which we need. And you can make this more clear rather than just doing an arbitrary term. Say we just use another assumption as the thing which is unlocking the judgment, and then going from the top to the bottom here, it's just an alpha renaming of the variable. So it really is just sort of computing to the identity. And it's only it's the fact that we've built a substitution into the co-unit rule, which is why we've ended up with a substitution here anyway. Okay. Oops. Okay, so these co-units, these things which sort of give us access to a variable from the context, are pretty close to being substitutions which just sit around waiting to be activated. So if you imagine a term like this, where we take a variable, we lock it, and then we use two different terms to unlock the same variable, supposing we've got a 0 and 1 around, then when you evaluate this, we amazingly create this argument and plug it in for x, then the unit matches with these two different instances of the co-units, and we end up substituting two different things for I in the two places that it occurs. And so this is quite unusual, that we've got a variable which is bound in a single location that ends up having two different things substituted for it in the end. But it's not quite just substitutions which wait to be switched on. So there's a different simple example where, again, we take a variable and then lock it twice, and then we use two different elements to unlock that variable. Then we can call this function in two different ways. Certainly, we're going to have to sort of amazingly bind something for both instances of the lock here. But then we can choose on the left whether we use the first one or the second one to substitute in for the variable x. And so if you sort of work through pushing these operations together, in one case you get the first thing, in the second case you get the second thing. And so if we get handed a term like this, the user of the term has some control over what sort of co-units end up getting used when you simplify. So it's not quite just sort of delayed substitutions or paused substitutions or something like that. Okay, so now I want to talk about how this relates to cubical. So this is going to be a bit, I'm going to have some, technical things on the slides, but my goal here is more to sort of give an impression, or give an idea of how we might use this type theory to help with an implementation of cubical type theory. So I'm going back to the first paper, first piece of past work, which I mentioned, which is this Lops paper, where they use the amazing right adjoint operation. Their purpose there is to build a universe that their overall goal is to build an internal model of cubical type theory. And the amazing right adjoint is important there in their construction of a universe which classifies fibrant types, so types that have the right structure to have the cubical composition. And they do this just in like ordinary intentional MLTT plus, so it's crisp type theory rather. So we need the flat modality and some axioms. So my goal is going to be a little bit different. I want to use the theory which I've described, which has this right adjoint built in without axioms, add a little bit more. So like some of the pieces of cubical, and then use the type theory to implement the rest of it inside the theory itself, rather than having it built into the implementation. So let me try and explain what I mean by that. So first of all, I'm going to just recapitulate some of the stuff that happens in this Lops paper. Specifically the place where they end up needing this root operation. So one of the parameters to the construction is a notion of composition structure, which is a structure that you can put on a line of types, which says what it means to have like composition and coercion along that line of types. And then for their internal model of cubical type theory, they define a type family to be fibrant over the base, which they think of as the context. So given a context and given a type family over it, they say that the type family is fibrant whenever there's a line in the context, there is a composition structure when you compose these things, there's a composition structure on the line of types. So the construction is not going to be really important here, but the point is that the construction that they do classifies crisp fibrations. Their axioms sort of have this flat modality as part of them. They can only really do this when all of the inputs are crisp, which, if you haven't seen it before, is what this the double colon means. And what it means is that a map from any type into this universe corresponds to a type family which is fibrant in this sense. So in the present type theory, you can calculate this this pullback very explicitly. So more explicitly than they do, because the construction gets stuck on some axioms. So the pullback that we're interested in works out to the following. So an element of this universe of fibrant types is just a type together with a term of the following thing. So root applied to the composition structure for this line of types. And sort of it's kind of essential that now that we're inside this root, we need some reason that we can talk about this X. And the fact that we're looking at a map out of the tiny interval here is what lets us talk about this X. So rather than so what this suggests is that we should change the definition of fibration that we're using to just be, well, a type is fibrant when we can give it one of these things, right? So the name that Grotzer, Weinberger, and Buchholz give to a property like this is amazing vibrancy, which I think is a great name. And we're going to say that a type is amazingly fibrant when we can equip it with an element of this. And the idea is that this structure no longer refers to the context. We're not saying that X is fibrant as a type family over some other type which we're thinking of the context. Rather, the thing that we're fibrant over has now faded into the background. We're now fibrant over sort of the ambient, unmentioned context, which the tiny type is now exactly what's letting us refer to. Okay. So the first proposal is like we try and do cubical type theory with this notion of fibrant. So to get this going, we're going to need to add some of the stuff from, let's say, Cartesian cubical type theory into this into this tiny type theory. So here are the things that I believe we're going to need. So first of all, we're going to need a universe of these like very special, very strict propositions called cofibrations, which have these extra judgmental properties. We're going to need to add a type former for cubical subtypes for these kinds of cofibrations. If you haven't seen these before, these are roughly like this cubical subtype is like a version of A, where whenever alpha holds the point, whenever alpha holds, elements of this are exactly equal to A naught. So this is not something that we can sort of reconstruct in the tiny type theory because it has this special judgmental property. And sort of similarly, if we're going to have univalence in a vibrant universe, we're going to need to put in glue types. I don't see a way around this either, unfortunately. But we're going to sort of relax things. We don't need these to be glue types for equivalences. We're going to use the weaker version where, stronger version, I suppose, where we just need a function. So I'm not really going to talk about this, so I won't say it. But importantly, what we're not going to put in is we're not going to put in coercion or composition. We're not even going to put in path because we can get it back from cubical subtypes. These are now things which we are going to implement ourselves in the type theory. Right. So the composition structure, which gets used in Cartesian cubes, we can just write down using the stuff that we have so far, sort of written explicitly. So written out, we're saying like we've got a cofibration representing the sides of a box, and we've got two horizontal locations in the box, and a partial element which exists at one of those locations and the sides. Then we can get one at the other place, which matches everywhere they're both defined. And so we can just take this and sort of plug it straight into our definition of amazing vibrancy. So what happens is we just stick a root out the front, and then everywhere that we previously had this line, we now, if we plug in the definition, the pieces of the definition of amazing vibrancy, it's now just, well, it's the type unlocked using certain things. Like in here, it's the dimension that we're composing along. And up here, it's the place where we, in the cube that we end up. And so now we play the same game as people who do the formalizations of these kinds of internal models, where we now have to show that this kind of vibrancy is closed under all of the constructors of cubical type theory. So these are the same kinds of things that people are used to. I've just written out one here to show how the lock gets involved. So what this would mean is, like, suppose we've got two vibrant types. So here what this means is just like two ordinary types and two elements of this amazing vibrancy structure. Then what we want to do is define the composition for the product. And so this means we're defining an element of the root. So the first thing we do is we lock everything to the left. So this means like all of this stuff here. And then we have the ordinary arguments of the composition operation. And in the definition, this is what you would expect, which is to compose in a product, we just compose in the two components. But we now have to make sure in all of these closure conditions that we can unlock the things that we need everywhere that we need them. So in these two components, luckily, we're doing a composition. So we're using an element of the root type, which means we gain access to this amazing argument, which is what we need to unlock the composition structures for the things on the outside that we're using.
Can I ask a quick question here?
Yes.
So on the left you have as first argument, so to say, you have a lock, and on the right you have like this upside down lambda.
Right.
Is the application behavior of like patterns different than that of an expression, or how should I think of this?
Of the difference.
Like on the left, you're defining it. Like you name what you define, right? And on the right, you give a definition. Is that the reason, or?
Yes, that's exactly it. So on the left,
Okay.
this is the pattern, or I suppose co-pattern, and on the right, we're giving the definition of the thing in that that branch. Yeah. So that I suppose it's a little bit unlucky in this example because I mean it's sort of like what we're used to with these kinds of co-pattern matching definitions of functions, where over here these aren't terms, right? These are variable names, and then over here these are terms which just sort of happen to be individual variables, right? So this is a co-pattern, not a term, and then over here these are terms. So in the patterns we have the locks, and then in the terms we have these amazing binders. Thanks.
But is it right that nothing funny is going on with like on the pattern line with the alpha and the R and R prime and T? Like, can I write comp of the lock equals lambda alpha, lambda R, and so forth?
Yeah, absolutely. So yeah, this could
Okay.
absolutely always be desugared into just a like iterated lock binders and regular binders. There's no sneakiness
Okay,
in
yeah,
this kind of
All right.
pattern. Yeah. I suppose I cheated a bit earlier with the sum example. You can sort of only get away with that if the sum is to the left of the lock. But yeah, hopefully you'll forgive me for that. Okay. So I'll skip the same sort of thing for sigma. The point is just that you just have to check that you can thread everything through where you need to. Okay, so now I'll just talk briefly about how you might implement this. So the main thing to think about is the unit and co-unit operations and like what to do about them. And you can always push them down to the leaves because they commute with everything. So the co-unit rule will get stuck once it gets down to a variable. Because, I mean, at this point, the co-unit is genuinely necessary for us to use that variable at all. There's only sort of one way to get stuff from out of behind a lock, which is to use the co-unit. And so we have to modify the variable rule to sort of build in an instance of this co-unit. And so depending on where the variable in the context is, you're going to need to provide possibly many terms of the tiny type to get past all of the locks in gamma prime to reach the variable that you actually want to gain access to. So here, this syntax just means that, well, these like double brackets are no longer true co-units. They're sort of part of the syntax of a variable usage. They're stuck. But over here, the type of this variable usage will be, again, a regular co-unit, which might then like push inside alpha in general, unless alpha happens to be a variable. Right.
So
unit, on the other hand,
if I can interrupt again, this is the co-unit of like of the adjunction between lock and root, or is it the co-unit of just because
no. It's the co-unit of the adjunction between extension with ordinary context extension with an element of the tiny type and context extension with a root.
okay,
So God,
with a
the
lock.
extension with a lock.
Yeah, okay.
Yeah. So all of the co-unit and unit rules, they don't mention the root operation at all. The only place that comes up is in the typing rules for the root, the root type. Yeah. Okay, sorry. So the unit rule never gets stuck as you push it down to the leaves. Eventually, as you do this, it's going to encounter the key that it corresponds to. There's sort of no way around the unit sort of meeting the corresponding key, because like sort of once you reach a variable, the the typing rule for this operation means that the variable that you've reached must be to the left of the lock that this thing corresponds to. And so there must be a co-unit there sort of waiting for it to sort of turn back into a regular substitution. Okay. Okay, so thinking about this very hard leads you to sort of an interesting kind of normalization by evaluation algorithm. So this is something that I've got a prototype for if you want to poke at it. So the idea is in ordinary normalization by evaluation, you're evaluating your terms in an environment which corresponds to like a semantic version of the context. But now our contexts have both variables and locks in them. And so we need a semantic version of the lock. And what ends up actually working is, just as a context extension is sort of pairing an environment with an additional value on the right, a semantic version of the lock is you just have an actual function from a value of the tiny type into environments, which are like, what is the environment you get when you apply the function for that lock to some argument. So the counterpoint to this is for like the neutral variables, they have they might have a whole sequence of stuck keys corresponding to co-units which sort of reached them and had nowhere to go. Sort of the interesting thing about these things together is when you do a variable lookup, you'll have a sequence of keys attached to a variable, and as you go through the environment, you'll encounter a sequence of locks, and you just sort of plug them together, and eventually you get an ordinary context extension, which is the value of the variable. So this sort of works out really nicely, I think. Okay. Okay, so this is my last slide. I'll just have some final thoughts. So why would this be so cool? Well, one of the reasons would be like, and this should have been at the top of the list, I suppose, is that I think it would really simplify implementations of cubical type theory if the notion of coercion and composition was no longer sort of built in behind the scenes. Like if you look at these implementations, there are some truly nightmarish files where they have to describe sort of in the internal core language the construction of coercion and composition for things like the glue type. And I have overheard people talking about what a nightmare that is. And it would be cool if instead like there was a much simpler core language with just the tiny type and some of those cubical things like cubical subtypes. That you then just use the language itself to implement these tricky things. One of the benefits of doing that is it'll be really easy to change the notion of vibration. So like there are several different ways of defining equivalence. And what you could do is you could just write different proofs that the glue type is vibrant, one for each version of equivalence, and just run do the same computation with each of them and see which one works best. I think that would be cool. You might also try some sort of more exotic versions of vibration, like the equivariant vibrations in the equivariant cubical sets paper. I imagine this would mean some more additions to the type theory, but I'm not an expert. And similarly with these directed vibrations that have come up in a few places. And sort of nothing stops you from having several of these going at once. There's an easy extension of the theory to one where you've got different tiny objects. You might have different intervals, which now sort of work independently. So this one's a bit of speculation. I would be interested to know if you could handcraft some proofs that glue is vibrant for specific situations that work better. So what I have in mind here is like the first thing you do in synthetic homotopy theory is you prove the successors and equivalents on the integers, and you get a path from the integers to itself. But that equivalence is of a very special kind, like it's between sets, and the proofs that it's an equivalence are quite simple. So what I'm wondering is, like, could you come up with a simpler proof that glue is fibrant for exactly this equivalence? It doesn't have to work in general. And could would that be helpful? I would love if some expert could tell me yes or no on that. I think it would be interesting to look at the normalization algorithm and see whether sort of lazily pushing the unit and co-unit around could make it work better, like maintain more sharing in the evaluation function. And then there are some like other non-cubical applications of tiny types, which would be great to look at too. So there's David Jazz, who's still interested in synthetic differential geometry. And so John Sterling pointed out to me that Fiore has some, and others have some work on higher order abstract syntax, which they model in exactly that category mentioned way at the start of functors from finite sets to sets, where the universal object plays a really important role. It would be nice to be able to formalize those sorts of arguments. Okay, and so that's the end of the talk. Thank you for coming along. I'll just scroll through the references really quickly.
Okay, thanks very much, Mitchell. So as usual, we'll do our visual applause or using the reactions in Zoom. And we have time for questions. So if you would like to ask a question, please just unmute yourself and go ahead and ask.
Okay, so thanks for the talk, Mitchell. This paper was on my queue, so I was very glad to see that I could just hear a talk about it first. So this question may not make a lot of sense, but the upside down lambda, has this sort of reverse binding, rule, which is of course the same as the rule you mentioned earlier. The true eliminator for pi types also is reverse binding, and there we can solve the problem by building in a cut with a weakened input. And so you obviously know that. And in fact, you use that exact move when you're in your side about the co-unit, right? So I guess my question is, why can't I also do something like that with the upside down lambda, where I somehow replace this anti-binding with some kind of application?
Well, so this anti-binding sort of is in the conclusion of the rule here.
Yes.
Whereas the thing we're trying to fix is well, not fix, but the thing which appears is that in the premise of the rule, there's an extra sort of unexpected variable. So there's sort of there's not, like, the conclusion already doesn't have the variable in it to be substituted for. Is there something?
I see. Yeah. No. Okay. Well, but then how is it that the lambda, the upside down lambda, is giving access to a variable to something else? Can you go back to that rule? Is this the rule? Or yeah,
So I'll go to this one because it's
yeah.
So this
Right,
rule
I
is
see.
giving the thing inside the eliminator access to an additional variable. So it's just the same as how, like, an ordinary lambda abstraction gives the body access to an additional variable. And that's not something you can sort of like substitute for to get rid of. It's kind of the same situation here.
Right. I see. Okay. Yeah. Thanks. Yeah.
Andreas has his hand raised.
Yeah. So I have not really a question, but some kind of paradox, I think, because as I argued yesterday, the co-unit of the transmission type. No, the unit of the transmission type basically performs some kind of variable capture, and this can never be like this can never commute with a variable contraction. But as this old paper by Jetter shows, you can actually implement the transmission type from the amazing right adjoint, so it should be somehow implementable in your system. And then your system does have like structural variables of type T. So somewhere in that reasoning there is something that I must be overlooking, but I think it's very interesting to look at this paradox closer. I think we can learn from
yeah,
that.
I would love to.
Yeah.
I'd love to try and figure that out. So this is something that isn't in the that is in the paper on the archive, is a an argument that you do get a dependent version of this operation just from this non-dependent one. I don't have a slide ready with the exact rules there for that. But so this is something that I glossed over. I don't know, as you were watching, you might have noticed that I've got an asterisk here when I've said that these types are closed. The inputs to a lot of stuff involving this root operation, to do this properly and not assume that they're closed, the inputs need to also be provided under a root, so that we can access them in the right place. It's kind of like how in the Lopes paper they need the flat modality to restrict when you can access certain things. A similar thing is here.
You're saying closed star means that f is actually of type root of the function type, or?
Yeah. And so,
So
like,
it's
not only
like an
that,
applicative.
but the types A and B themselves have to be elements of root universe to get access to them in that way. And so the version of transpension which I get from this kind of type former also has its arguments protected by having root around them. And I'm wondering if that kind of restriction somehow gets around the thing that you're worried about.
Maybe.
Yeah, I'm not sure. Sorry.
Thanks.
Yeah, Steve, go ahead. Unmute.
Okay, thanks for that. That was really nice. I've been kind of hoping to see some more syntactic work on adding the root operation into the type theory, and you've shown us how challenging it is, but you seem to have a system that is working, so that's great. I can say a little bit more about the prehistory of using the root operation and the tiny interval before the Lopes application. Thierry and I were both working on cubical models of homotopy theory and homotopy type theory. And I don't know where Thierry got the idea from. He could say maybe, but I got it from Bill DeVere. So I think that's important to record. Bill's idea was we use cubical sets, and not just any old cubical sets, but Cartesian cubical sets, because the interval is a tiny object there in the Cartesian cubes. And he's working by analogy to SDG, where the tangent space is exponentiation by the tiny type D. And Bill stressed the path space will be exponentiation by the tiny interval. And that analogy, he thought, was a very useful one, and we should make use of that in homotopy theory. So he was stressing this for 30 years in lectures, and then I pursued that with him a little bit privately in conversation several times. After I started doing homotopy type theory, I discussed it with him a few times, and he suggested that that's something we really should do, is we should use the Cartesian cubical sets to model homotopy theory because of the tininess of the interval. So at least through me, that idea goes back to Bill. Thierry can say where he got it. Maybe he had the same insight or something like that. So I just wanted to throw that out there.
Thanks.
Shall I comment on this? Or? Yeah.
Sure.
Yeah. So I got this. I mean, talking with Christian Sattler, trying to understand. I mean, how we can get a model of univalence, and what was the key point. Christian pointed out that the tininess of the interval was really the key of the thing. Yep. Thanks.
Well, I'm sure Christian got it from me, I'm sure. So,
Okay.
I mean, I was talking about it for many years before I think when Christian was still in knee pads. So anyway. But like I said, I got it from Bill, so.
Okay, it's time for more questions. Maybe you can say a couple of words about this implementation you linked to. How much is implemented there?
So I have a type checker. There's no, which involves like a doing proper normalization and conversion checking. But there's no like elaborator or anything like that. So if you look at the examples in that repository, it's very painfully spelling out the type of every little thing, which is necessary.
Yeah, but that's still a good proof in principle that it works.
Yeah.
Excellent. Do you think? I mean, do you plan that this might elaborate into something more advanced, or do you hope that it might be adapted into an existing proof of system?
That's a good question. I mean, to end up with something industrial strength, I think there would need to be more people who knew what they were doing involved. But the type theory itself is sort of strange enough that I'm not sure it would be a good idea to try and mash it into an existing proof of system. So I'm not sure. It could be.
I mean, cubical type theory is quite a change from non-cubical, and it was brought into AGDA.
That's true. I need to look at the how they do modalities, I suppose.
Okay, Andy has a question.
It's just a comment, really, because so I could remember sitting in an apartment in Aarhus in, I guess, 2022, working through that construction of, universe of vibrant things using the tiny stuff, which we did indeed get from Thierry and Christian Sattler, who I'm sure stole it from Steve and Bill. But what I was going to say is the reason it all worked for me, because the arguments were, you can do them diagram chasing in the end, but it's kind of complicated. Definition is, vibration is complicated. So I was very fortunate because Bas Spitters was in communication with Andrea Vezzozzi, who was at that time adding bits of modal type theory to AGDA. So Bas twisted Andrea's arm to give us the right modal type theory. And I used that, version of AGDA, not that it wasn't, it was an unofficial hack of AGDA, but it was absolutely essential. I couldn't have sort of got through and been confident that we got the results in the paper without using that. So I do exhort you to find the equivalent of Andrea Vezzozzi or whoever, and AGDA is probably your best target because it's kind of the one that gets hacked the most often, and try and get them to give you. It'd be very cool to have what you were talking about available to experiment within AGDA. Yeah. I mean, especially since you can never get used to the syntax unless you can kind of start using it. I mean, just the user feedback, I was quite confused by your notation for the unit and co-unit because I was thinking somehow they were actual substitutions, but they're actually just some sort of explicit substitution notation, aren't they? Yeah.
Right.
Anyway.
Yeah.
So that was just a bit of history. Not really a question. Sorry. It was a very nice talk, though. Thank you very much.
Oh, thank you. I've gone around and around on what syntax to use for these things, and it's.
Oh well, all right. So I have a
has
comment. I'm going to make a comment, right? So even though I'm an
Please.
author on a paper that has the lock symbol in it, I hate it. Right. And I hate even more that you're using a key symbol. I wish you wouldn't use either.
Well, I'm happy to it's just a LaTeX macro. I'm happy to switch it to anything you like. It's I found it really difficult to come up with syntax that it was possible to remember, and sort of had at least some kind of rationale behind it. But I'm very open to suggestions, because I know that it's just as is. It is quite noisy. So
I've learned over the years that one never should criticize somebody else's choice of concrete syntax, because it never does you any good.
If you're interested in doubling down, I've seen a paper, I think like a joke paper that uses like the laughing emoji for some symbols.
Well,
You really wanna...
something I was thinking is I could always do like blue and orange portals for like the variables sort of appearing in one place, appearing in another. So
that could be fun for a very specific reader.
Yeah, probably.
Okay, so maybe now that we're getting into notation, this would be a good time to close off the session. So let's all thank Mitchell again. And this is the last talk of the season, so I hope to see you all in the fall. Okay, thanks.